Sulfuric acid is an important chemical used to make detergents, fertilizers, and dyes. It is manufactured in a multi-step process. Part A. In the first step of the manufacture of sulfuric acid, sulfur dioxide can be made from the combustion of hydrogen sulfide, shown in reaction 1. Part 1. Explain why the enthalpy change for reaction 1 has a negative value. Use ideas about enthalpy changes associated with bond breaking and bond making. The reason why reaction 1 has a negative value is because it's exothermic, and that means that more energy is released by forming bonds than required when breaking bonds. To get the mark for this question, you need to write this statement: more energy released by forming bonds than required when breaking bonds. This gets you the mark for this question and explains why reaction 1 has a negative value of minus 1125 kilojoules per mole. Part 2. Some standard entropy values are given below. Using calculations, explain whether reaction 1 is feasible at 20 degrees Celsius. For this question, we're going to be using the equation delta G equals delta H minus T delta S. And we need to work out delta S first, which is the change in standard entropy values. So using the equation and the entropy values in the table, we can work out delta S. And that would be delta S equals brackets 2 times 248, because what we're doing is we're working backwards. So we're going to do products minus reactants. So that's part of our products, our 2 times 248 plus 2 times 70, because that's our standard entropy change or value of water. And then minus 2 times 206 plus 3 times 205. And that equals a standard entropy change, or the difference in standard entropy changes, of minus 391. And this is measured in joules to the Kelvin minus 1, moles to the minus 1. Or if we were to convert this, it would be minus 0.391 kilojoules, Kelvin to the minus 1, moles to the minus 1. So then working out delta G, or Gibbs free energy, that would be minus 1125, which is the value of delta H that we've been given in the question, minus 273 plus 20, because that's our temperature in Kelvin. 20 degrees Celsius plus 273 converts degrees Celsius into Kelvin, and then multiplied by minus 0.391, and that equals a delta G value of minus 1010 kilojoules per mole. And so this means the reaction is feasible, and the reason behind this is because our delta G value is less than 0, and this means the reaction is feasible. In this question, you get a mark for working out delta S, a mark for using the Gibbs free energy equation, or delta G equals delta H minus T delta S. You get a mark for working out delta G correctly, so minus 1010 kilojoules per mole. And then you finally get your fourth mark for saying that the reaction is feasible because delta G is less than 0. Alternatively, you could say that it's feasible because delta G is negative. Part 3. Calculate the standard enthalpy change of formation of hydrogen sulfide using the enthalpy change for reaction 1 and the standard enthalpy changes of combustion below. For this question, we've got to construct a Hess's triangle. So that means we're going to use our enthalpy changes of combustion to construct this triangle. So if we combust sulfur, we get sulfur dioxide. So that means we're going to have an arrow from 2s and then plus some oxygens, and that's going to produce sulfur dioxide. And so we write minus 296.8 times 2 for this arrow, because we've got 2 is the stoichiometry. Then for water, well, that's the combustion of hydrogen. So that's going to be equal to minus 285.8 times 2, and we need to add some hydrogens to the bottom of our Hess's triangle. And then we want the formation of hydrogen sulfide, which is what we've been asked in the question to calculate the standard enthalpy change of formation of hydrogen sulfide. So that will be using the bottom of our Hess's triangle to work out or use and create hydrogen sulfide. Balancing the bottom of this Hess's triangle, we need 2 hydrogens and we need 3 oxygens. And we can label the standard enthalpy change of formation of hydrogen sulfide as 2x. And then we can also label minus 1125 as the enthalpy change of reaction. So then working out the enthalpy change of formation, we need to go this way around our Hess's triangle. So as I've indicated with this green arrow. So that would be minus 296.8 times 2 plus minus 285.8 times 2 plus 1125. What I've done is I've reverted the sign from a minus to a positive for the enthalpy change of reaction. And that's going to equal minus 40.2 kilojoules per mole. And that equals 2x. So if we were to work out x, that would be minus 40.2 divided by 2, which equals minus 20.1 kilojoules per mole, which is what we can write on the answer line for this question, minus 20.1. For this question, you get a mark for your broad equation of all the values in your Hess's triangle, so not actually finding its answer, but our minus 296.8 times 2 plus minus 285.8 times 2 plus 1125, that gets a mark. Your second mark is from correctly working out 2x, so writing that this equals minus 40.2 kilojoules per mole. And then your third mark comes from working out x on its own, or the standard enthalpy change of formation of hydrogen sulfide on its own, and that would be minus 20.1 kilojoules per mole. Gets you your third mark. Part B. The second step in the manufacture of sulfuric acid is the conversion of SO2 into sulfur trioxide, SO3, using equilibrium 1. An industrial chemist carries out some research into equilibrium 1. The chemist fills a 10.2 decimeter cubed container with SO2 gas at room temperature and pressure, and then adds 12.0 grams of O2 gas. The chemist adds the vanadium 5 oxide catalyst and heats the mixture. The mixture is allowed to reach equilibrium at a pressure of 2.50 atmospheres and a temperature of 1000 Kelvin. A sample of the equilibrium mixture is analysed and found to contain 0.350 moles of SO3. Part 1. Write an expression for Kp for equilibrium 1. Include the units. When working out Kp, you use your equilibrium expression and you work backwards. So you have your products as your numerator and your reactants as your denominator. I'm talking about this in the idea that our reaction is going to go forwards. So what that would be is our product would be SO3. So we would have SO3, and we're going to square this because we've got a big 2 in front of the SO3. And then because we're talking about Kp, we're going to have the partial pressure. Then we're going to divide by our reactants. So we'd have the partial pressure of SO2, and we're going to square this because of the big 2, and then multiplied by the partial pressure of O2. And that's going to equal Kp. So now we need to think about our units. So each partial pressure is going to be measured in atmospheres in the question, because that's what we've been told that the overall pressure is. So if we had atmospheres squared, and then we're going to divide that by atmospheres cubed because we're squaring and then timesing by another pressure, so that's going to be cubed. Well, then we can eliminate the numerator and 1 of the denominators, so that we're left with 1 over atmospheres. So another way of writing this is atmospheres to the minus 1. To get the 2 marks for this question, you get a mark for your expression for Kp and a mark for having the correct units, or atmospheres to the minus 1. Part 2. Determine the value of Kp for equilibrium 1 at 1000 Kelvin. Show all your working. Give your answer to 3 significant figures. Firstly, we need to highlight the key pieces of information that are going to help us answer part 2. So our first key piece of information is that we've got 10.2 decimeters cubed of SO2 and we're measuring this at room temperature and pressure. Then the fact that we've got 12 grams of O2 is our next key piece of information. Also the fact that the total pressure of the system is 2.5 atmospheres and that at equilibrium we have 0.35 moles of SO3. So that means our first step is going to be to work out the moles of SO2 and O2. So we're going to use 2 different equations. Our first equation is volume in decimeters cubed, and this is going to be divided by our molar volume of 24, and that's going to equal moles. So for SO2, so our N of SO2, that's going to be 10.2 divided by 24, and that equals 0.425 moles. Then we're going to use the equation triangle of mass divided by relative formula mass multiplied by moles. And we're going to do this to work out the moles of oxygen. So the moles of oxygen, that will be 12 divided by 32. 32 is the relative formula mass of O2. And that's going to equal 0.375 moles. Then we're going to use ICE. This is an acronym for working out the moles at equilibrium. So we've got our initial moles, our change in moles, and our moles at equilibrium. So our moles at equilibrium for SO3 is, we've been told in the question, 0.35. So that means we've got a change of plus 0.35, and initially there would be 0. Initially we have 0.425 moles of SO2 and 0.375 moles of O2. And then we're going to minus 0.35 from SO2 and get 0.075. We're minusing the same amount that we've added in our products because it's a 2:2 ratio. So looking at the stoichiometry in the equation, we've got the same portions. But for O2, we're going to minus 0.35 divided by 2, and that's going to equal 0.2. So then using this to work out our total moles is just our moles at equilibrium added together, and that is going to equal 0.625 moles. So we can use this to work out partial pressure. So partial pressure has the equation, if we were to write this out, partial pressure equals the mole fraction, and the mole fraction is the amount of moles at equilibrium divided by the total moles. So mole fraction times total pressure. And our total pressure for this system is 2.5 atmospheres. So working out the partial pressures, we can do the partial pressure of SO2, and that is going to be equal to 0.075 divided by 0.625 multiplied by 2.5. That equals 0.3 atmospheres. Then working out the partial pressure of oxygen, that is going to be equal to 0.2 divided by 0.625 multiplied by 2.5, and that equals 0.8 atmospheres. And finally, the partial pressure of SO3, that's going to equal 0.35 divided by 0.625 multiplied by 2.5, and that equals 1.4 atmospheres. Then using our expression for Kp, we're going to have 1.4 squared divided by 0.3 squared multiplied by 0.8. And that is going to be equal to 27.2 atmospheres to the -1, which is what we can write on our answer line, and this is our value for Kp to 3 significant figures, which we've been asked to give our answer to in the question. To get the marks for this question, you get a mark for working out the moles initially of SO2 and O2. You get a mark for using ice or working out the equilibrium amount of moles for SO2 and O2. You get a mark for working out the total moles. You get a mark for working out the partial pressures of SO2, O2 and SO3. And you get a mark for correctly working out the value of Kp to 3 significant figures, so 27.2. Part 3. The chemist repeats the experiment in B at a different temperature. The chemist finds that the value of Kp is greater than the answer to B Part 2. Explain whether the temperature in the second experiment is higher or lower than 1000 Kelvin. So, because a greater Kp value is found than the answer to B Part 2, this means that the equilibrium position is going to shift to the right. And so that means that we're going to use a lower temperature. We're using a lower temperature because the forward reaction is exothermic. And we know that it's exothermic because its delta H value is negative. So that means it's going to be an exothermic reaction. To get the 2 marks for this question, you get a mark for saying that a greater Kp value means the equilibrium position shifts to the right. And your second mark is from saying that a lower temperature is needed because the forward reaction is exothermic. This gets you your 2 marks. Part 4. Explain the significance of the expression Kp is bigger than 1. The reason that this expression is true is because the equilibrium position lies far to the right. To get the mark for this question, you must write this statement. The equilibrium position is far to the right. Part C. Vanadium 5 oxide V2O5S is used as a catalyst in equilibrium 1. Part 1. Explain how the presence of V2O5 solid increases the rate of reaction. Include a labelled sketch of the Boltzmann distribution on the grid below and label the axes. So firstly, labelling our axes. Our x-axis is energy, so if we add this label on, and then our y-axis is the number of molecules. So here we've labelled our axes. Then the Boltzmann distribution, well, this looks a bit like a peak and then it levels out and sort of plateaus. And then if we were to label our activation energy without our catalyst, and then our activation energy with our catalyst. And what has happened is that our activation energy has lowered and it has shifted to the left, meaning that less energy is required. So the reason I've done this is because we're told in the question that vanadium oxide is used as a catalyst. Then we need to explain how this increases rate of reaction. So there's a statement that we can write that explains why a catalyst increases the rate of reaction using what we know about the Boltzmann distribution. And that is that more molecules will collide with an energy above the activation energy. That's because with a catalyst, our activation energy has shifted left, and so it's less energy. And this is with a catalyst. So we can write this statement to explain why it's increasing the rate of reaction. To get the marks for this question, you get a mark for correctly labelling your axes, a mark for having the correct general shape of a Boltzmann distribution curve, a mark for correctly identifying that the activation energy with a catalyst is shifted more to the left, or labelling this on your Boltzmann distribution curve as we've done here. And then you get your 4th mark for writing the statement that more molecules collide with an energy above the activation energy. And this is related to why the presence of a catalyst increases the rate of reaction. Part 2. Explain whether vanadium 5 oxide is acting as a homogeneous or heterogeneous catalyst. Vanadium 5 oxide is acting as a heterogeneous catalyst, and that is because the catalyst is in a different state from other substances in the reaction. To get the mark for this question, you must say heterogeneous and then why it's heterogeneous, and that's because the catalyst is in a different phase or state.